So we have a great pleasure to have Martin here. You know, Martin is the new generation of MIT, and he's doing a wonderful work in many, many aspects of cold atoms and atoms in the lattice, fermions and everything. So everybody knows Martin, so I'm just going to ask you to start your talk.
Okay, thanks so much. So, am I too loud here? Okay. So it's a great pleasure to be here at this wonderful occasion to celebrate Dan's birthday with everyone. Thanks, Wanderlei, for the wonderful organization of the conference. I will be talking about what happens in a fermionic superfluid. We have heard some about bosonic superfluids already. And namely, what happens when you create effective particles inside, which we call solitons. And turns out these guys propagate in our gas, and I will tell you what these lines mean. And it turns out they're very heavy, so that's what explains the title. But of course, I have to give you a whole story about it. Let me first say that I'm extremely thankful and grateful to Dan for the creation of a big, big family that is the center of ultra-cold atoms, where he brought together people from two universities that, as I hear, did not always get along so well. So the Center for Ultra-Cold Atoms was an amazing merger of these two disjunct worlds, and now we're all friends and happy and meet every week. It's just a wonderful, amazing family. It's like pairing, right? Yeah, it's like fermion pairing. So thank you, Dan, for that wonderful family that you created for us, and where experienced researchers and the young kids who are green behind the ears get a chance to do research together. And it's just a wonderful atmosphere. So, as we know and already heard about, particles at low temperatures, of course, should be described as waves. And as I cool the gas, amazingly, the uncertainty in the position of these particles grows and grows, and at some point we know that we are in trouble. We know we are in trouble because now, as these wave functions start to overlap, quantum statistics comes into play and plays center stage. And we know that there are now two things that we have to know. We have to know that there are two kinds of particles, fermions, which absolutely hate each other, and the bosons that love each other. The fermions, you see, they're each doing their own thing. Each of them is occupying their own energy state. This one is listening to music. This one is spying on the others. You know, not very nice social people. This one is Pauli blocking himself. It's terrible. Whereas these bosons, they like to party. They like to go into the ground state of the system and form a Bose-Einstein condensate. There they say, "Happy birthday, Dan, and thanks for condensing us." So clearly, these are hydrogen atoms. This is what happens to them at low temperatures. In the cartoon picture, they all start to form this one giant macroscopic meta wave. Whereas the fermions, hating each other, they have to stay apart from each other and avoid each other at all cost. But well, if you look at the difference between bosons and fermions, there is actually a way to connect these two apparently completely disjunct worlds. The bosons here, they like to occupy the ground state. The fermions occupy these energy states singly and have to avoid each other, so you might think they are different worlds. But let's look much more closely into these bosons, then you will see, wait a second, they are fermion pairs. Hydrogen, Dan's favorite atom, is an electron glued to a proton. Sodium, another atom that we really love in the hallway of Building 26 at MIT, you can think of it as a sodium ion glued to an electron. And what we love also is lithium-6 atoms glued to other lithium-6 atoms forming a lithium-2 molecule. So bosons are strongly interacting fermion pairs tightly bound. And well, on the Fermi side of things, I just need to put another species of fermions next to the red ones. Let's call the red ones spin up and the blue ones spin down, and they will pair up as well for the weakest interactions, in fact, and form what we know as a Bardeen-Cooper-Schrieffer superfluid. These two worlds are beautifully connected, in fact, by a crossover, where you cross over from the limit of tightly bound molecules, which is a Bose-Einstein condensate, to the Bardeen-Cooper-Schrieffer state of long-range Cooper pairs, going through what we call a crossover superfluid, where the pair size is in fact on the order of the interparticle spacing. So these pairs, these fermions probably have to change partners frequently. There should be a lot of fluctuations going on in this interesting gas. Well, to prove that you have a superfluid, what you should do is you should rotate it. If you're ever in doubt that your coffee is superfluid or not, just give it a spin. And then as you do this, you should see that there are vortices appearing in the superfluid, quantized vortices that carry single units of circulation given by h bar Planck's constant over the mass of the bosons, fermion pairs. And this is exactly what we did a few years ago with our lithium-6 gas. We had 2 spin states of lithium-6 in our atom trap. We took 2 laser beams as a spoon, swirled it around a couple of times, and waited a few seconds. And out came, indeed, a beautiful vortex lattice, demonstrating that this is indeed a superfluid of fermion pairs, a macroscopic wave function describing these pairs. And this worked in the entire regime from tightly bound molecules to the regime where pairing is due to many-body physics, the BCS side of things. How do we tune this? Well, this is the long story, or the wonderful story of Feschbach resonances, where we can tune the interactions between these fermions at will just by a knob in the lab, which is the magnetic field, allowing us to tune from a tightly bound molecule to a long-range Cooper pair. So this established that particles behave as waves, even in the case of fermions. But now, there is an interesting way how to invert this. You can actually make particles out of waves. You take just a bunch of waves, sum them all up, and you get a localized wave, if you just do it right. And under certain circumstances, you can describe this localized wave as a particle carrying an energy and a mass. And this is a principle that we use in physics all the time. Think of Landau's quasiparticles, describing a strongly interacting system of fermions as a weakly interacting system of quasiparticles. The Higgs particle is another example. Polarons, which are dressed impurities swimming in the sea of others, forming an effective particle. Cosmic strings you could name, or the vortices that I just showed, and solitons, the topic of this talk. So let me introduce solitons. Those are waves that do not disperse because their dispersion is cancelled by a nonlinearity in the waving equation that governs their propagation. You have this in water waves because water waves are described by a nonlinear wave equation. And so you see these wonderful waves that are not spreading and can actually propagate for kilometers. You see it in structures of clouds of in air. Turns out, I must admit, never seen that myself. But the internet knows about it, and so I put it there. This person, fantastic, built this coupled pendulum and shows a soliton propagating on it. So you can do it at home if you want. Or you do it in optics, in fibers, where solitons can also propagate as nodes in the electromagnetic field. They also exist in superfluids, because superfluids, no surprise, they are described by one big macroscopic wave function. And, well, a wave function, it's just like a rubber band. You can twist it on one side of the cloud, you twist it, give it a phase shift of pi, or 180 degrees, and then you have a node in your wave function where the wave function completely vanishes. That means the square of the wave function vanishes here. And in the case of Bose-Einstein condensates, you will there find no particles whatsoever. So here there will be no particles, and over here the density will be back to the background density. To be more formal, there is a wonderful equation that describes Bose-Einstein condensates. We love it, the Gross-Pedersky equation, where here you see the dispersion, here you see the nonlinearity, and all that has to equate to the energy times the wave function itself. So it's a nonlinear Schrödinger equation, which can be beautifully solved by the tangent hyperbolicus, which is shown here, which changes sign from negative to positive. And it's exactly 0 here for the stationary soliton that I'm describing. And indeed, the density drops to 0 at the soliton. And the length scale over which that happens is the characteristic length scale for these Bose-Einstein condensates, the healing length. So now this can actually be created in the lab. And Bill Phillips' group and Klaus Sengstock's group about 13, 14 years ago managed to create those solitons using a phase imprinting technique that I think was borrowed from Eric over here, where he did used it to make vortices actually. And these guys said, well, we can make solitons. And they imprinted, using a laser beam, a pi phase shift on one side of the cloud by just taking a laser beam that shines only on one side of the cloud, but not on the other. And so the phase is advanced to pi, if you tune it right, and you create a soliton that then propagates happily as a dark feature in your superfluid. So this works. These things are alive. They're real particles. And turns out, since they're effective particles, they must have an effective mass. And so if you put them in a trapping potential, and they have to be in a trapping potential because your superfluid is in a trapping potential, they have to oscillate. Now the question is, what is the frequency of oscillation of these effective particles? If you think very quickly, you might think, well, the soliton is a location of missing particles, so negative mass. So that means probably they experience this trapping potential, which is exactly the negative of the trapping potential of real atoms. And so probably they will just oscillate at the very same frequency as positive mass particles. Turns out it's not the same frequency. There is a wonderful contribution of superfluid backflow. The very fact that the phase changes across the soliton means, in quantum mechanics, you know what a phase gradient does. It gives you velocity. So the very fact that you have a phase gradient across the soliton means there has to be superfluid backflow across the soliton. And that you also have to carry around with you. Not only this depletion of atoms, which is negative mass, that's right, but also the superfluid backflow. That doubles up the effective mass of the soliton, and in fact, the period of oscillation, therefore, turns out to be squared of 2 times longer than the period of oscillation of a single atom in your trap. So that has been seen in Klaus Sengstock's group in 2008 and Markus Oberthaler's group in the same year. This propagation is fully explained by the Gross-Pidevsky equation, the time-dependent Gross-Pidevsky equation, and it's a beautiful example of nonlinear waves propagating in Bose-Einstein condensates. Now, what is different when you have solitons in a fermionic superfluid? In one slide, I have to explain to you Bcs pairing, so let's do it. This here is simply the parabola of free particles, p squared over 2m that we all love, but I shifted the parabola down by 1 Fermi energy because I want to fill my trap with a certain number of fermions up to, well, the Fermi energy, and so I shifted this parabola down. Now, what happens in Bcs pairing is that you have to not only consider the particles that live down here, below the Fermi energy, which is this line, but also the holes. You can consider the holes to be effective particles, again, with which you can couple. And a spin-up particle of momentum k, coupling and pairing with a spin-down particle of minus k, is effectively kind of the same thing as a spin-up particle of k coupling to a hole of that same momentum k. So, well, we know in atomic physics what happens. You get an avoided crossing. So, in fact, Bcs pairing is nothing else than an avoided crossing that we all love in atomic physics. If you look closely in this area here where we have opened up the gap, which is, by the way, called delta in the next slides, you see that I could probably describe this region here as a Dirac equation, where I have 2 linear dispersions that are then coupled by an effective mass, which is given by precisely the pairing gap. So that's what happens, that's what we will do. The Dirac equation has a name in the theory of superconductivity. It's the Andreev equation. And indeed, you have a linear dispersion for your spin-up and spin-down particles, the particles in the holes. There is this gap term here, which plays the role of the mass in the Dirac equation. But now, since we want to make a soliton, this mass is going to change its sign. in space. So you might think I'm crazy, you know, a spatially changing mass, no one has thought of that. That's crazy. No, 1976, Jacques and Rebbe actually thought about what happens when you have a spatially changing mass. I don't know why they thought that, but it's amazing. And they figured out that if you have such a situation in the Dirac equation, you always find bound states that live right there at the zero crossing. And these bound states in their theory, in Dirac theory, they have zero energy. So effectively, what happens is that the gap squared forms kind of a potential for these bound particles, and they live there. Those are these Andreev-bound states. They don't have exactly zero energy because, well, you see there must be an energy cost for forming this state, but it's connected to the story of relativistic quantum field theory in 1976. It's kind of cute. Now, I couldn't resist showing this slide from someone that we know very well, Harold Hess, who was mentioned just in Jok's talk as the person who actually figured out evaporative cooling. A few years later, he did an amazing experiment in condensed matter where he took a scanning tunneling microscope, went inside a vortex core, and saw that as the tip is moving inside the vortex core, you see this peak inside the vortex core as you tune your STM voltage around. Inside the pairing gap, those are the Andreev-bound states. So the same Harold Hess that did the evaporative cooling also provided wonderful evidence for these Andreev-bound states living inside vortex cores. So now for us, in this fermionic superfluid, we realize the soliton is a zero in the gap. The gap goes to zero at the soliton, but that doesn't mean that the particle number goes to zero at the soliton. It's not like in Bose-Einstein condensation. The only thing that we lose in the soliton are the Cooper pairs. Only those go to zero. The rest, the normal guys, stick around. And so the soliton has a dip, a density dip, which doesn't go to zero. It's actually very shallow, only a small fraction given by the gap divided by the Fermi energy. That small fraction, only that is lost, and the soliton is almost completely filled with normal fluid. That means we can also figure out what then the what the bare mass of the soliton is. It's just the mass of the missing atoms. That was the naive contribution that we discussed in the case of Bose-Einstein condensates that we thought should lead to a period that is equal to the period of free atoms. We will see this is not the case for the soliton again. Here you just count whatever is missing here, so it's given by the number of particles that would normally sit in the soliton times this ratio gap over E Fermi times the mass of a single atom. So those are just the guys that are missing. But what is now the true effective mass of the soliton? Well, I told you that a big contribution that we naively forgot but have to remember is this backflow that has to occur across the superfluid. Just the very fact that the phase of the superfluid changes by, say, delta phi as you go across the soliton. And you can simply calculate how much momentum that carries around with it. It's just the mass of the particles times the density times the integrated velocity across the soliton. And you all know that the velocity is just the gradient of the phase times h bar over 2m because we have fermion pairs. So you get a momentum which just is directly proportional to the phase shift across the soliton. Now, how to get the mass? How to get the mass from a momentum? Well, I have to check how the momentum changes with velocity. dp du, that gives me the mass of the soliton. Now, this little calculation here is actually conjecture, just looking at numerical calculations for such a soliton in the BCS regime. I see that the phase is roughly linear in velocity, where the characteristic slope is given by the speed of sound of the superfluid. Believe me, this simply means that practically all atoms that are stuck inside the soliton have to move with it. So it's very heavy, actually. Much more atoms than the ones that are missing. And so that gives me immediately a mass enhancement that is much larger than 1. The effective mass is much larger than the effective mass, probably going like E Fermi over the gap. and the period should be increasing tremendously, going just with the square root. This is again where it's helpful to have been in Dan's atomic physics course, just like Eric said yesterday, because he told us we should measure frequencies whenever we can, because that gives us precision. That's exactly what we will do. So here's the prediction for the Soliton period versus the interaction strength in this BEC-BCS crossover done by the group of Sandro Stringari and Lev Pitajewski in Trento. They predicted that due to this filling with Andreev-bound states, the period should increase quite dramatically from this square root of 2 solution up to well beyond 2 times the bare period of oscillation of these atoms in the trap. So this was intriguing enough that we thought we should check this. So, well, we went back to just try to imprint a phase, just like what was done on Bose-Einstein condensates, using a laser beam that shines on half of the cloud for a certain time t, with a certain potential u, and that will give us now a phase gradient, a phase shift from this side here, between this side and the other side of the superfluid, of 2 times ut over h bar. The 2 is because we have 2 fermions making up our pair. So that actually works. Here you see now, hopefully, a movie of what happens right after we imprinted this pulse. If you squint your eyes, you can see a slight density depletion moving up and down inside our superfluid. So this is the soliton that we are after. And here you see the frames of the movie, and rather clearly this density dip which is oscillating in the trap. You see the period is very long, on the order of seconds, and let me tell you, this is actually already many times our trapping period, which is on the order of 100 milliseconds. So, something is very heavy here. Turns out there is a difficulty in imaging these solitons because, as I said, they're filled. In fact, on resonance, right at the Feshbach resonance, where the interactions are strongest, and you might think maybe the system is most interesting, you don't see the soliton in absorption images. There is no visible density dip. What you have to do is you have to move to the BEC side of the Feshbach resonance. You have to take these long-range pairs and glue them together into tightly bound molecules. At the same time, you reduce the interactions and empty out the solitons so that now they become visible. So this is the imaging technique that we can use to visualize solitons even on resonance or on the BCS side of the crossover. So now here again the slides from the movie. We can subtract the average of these images, smoothing away the solitons and taking the difference. There you see it almost looks like bacteria, which have some funny defect. And turns out this is just a short cut out of a many seconds long oscillation of these solitons, these effective particles moving in our fermionic superfluid. So these are extremely robust particles. If we are on the BEC side of the story and we look at the period, we see actually it's already quite a bit longer than the period of bare atoms, much longer than square root of 2. So already a strongly interacting Bose gas does not give you square root of 2, it gives you already a much larger period and much larger mass. And as we go to the Feshbach resonance, as we increase the interactions, the period of oscillation gets longer and longer, telling you that the effective mass of these particles is larger and larger. And these are the results where we plot the soliton period normalized by the trapping period as a function of the interaction parameter. On the same scale, on the same graph, I can just also reinterpret this as the effective mass enhancement, m star over m, by just squaring this, and I see the effective mass enhancement is on the order of 200 on resonance, much larger than the predicted 3 that came out of the mean field theory of Stringari and Pitajewski. We did check that this doesn't depend strongly on aspect ratios. In fact, we believe that for the longest aspect ratios, we are in some kind of quasi-one-dimensional limit. So that is not an explanation. We also checked that temperature doesn't play a big role. At low temperatures, we see, of course, beautiful oscillations and a very clear contrast of the soliton. At higher temperatures, the first thing that happens is that you get anti-damping. Might be very confused. Normally, an oscillation should die out. This one actually grows. Well, the soliton is a negative mass particle and will increase in amplitude. It can lower its energy by speeding up, and therefore you see anti-damping. And at even higher temperatures, we start seeing, well, at the same time, lots of wiggles and ripples in the cloud, which might actually be thermal solitons. And at the same time, the lifetime goes down, and the soliton position is no longer very well defined. However, as long as we see the oscillation, the period stays the same. The anti-damping time goes down, the lifetime goes down, but the period stays the same, so this shows that this is actually a quantum effect, the large enhancement of the mass. We think it is due to quantum depletion, non-condensed bosons that also live inside the soliton that enhance the mass in addition to UNJF-bound states. So with that, I would like to conclude. I told you about the first observation of solitons in fermionic superfluids. The relative effective mass is 50 times higher than mean field theory. Now, this is good news. We don't agree with theory. I love that. Mean field theory was doing a good job for thermodynamics. It was kind of within a factor of 2, but it was okay. Now, here we are completely off, factor of 50. So that's a wonderful challenge to theory to figure out where that factor of 50 comes from. In the future, we hope to do fun experiments where we take two solitons, collide them with each other, make soliton trains, and in the presence of spin imbalance, even maybe see something like a metastable full de Ferrel state of oscillating Cooper pairs. So I would like to thank you for your attention, showing the wonderful team that worked with me at MIT and the CIA, which was created by Dan and provides a wonderful home to all of us. Thanks very much.
You showed a simple model at the beginning where it looked like you were predicting the effective mass would scale as the Fermi energy over delta. So in the BEC limit, that should go like something like a squared. And it didn't look like it had that dependence at all. Could you explain that?
So you're using my prediction for the BCS limit for the BEC limit, which is unfair.
Well, shouldn't the same argument that you gave in the BCS side apply to the BEC, but even more so? I would expect that argument would be even more correct, because then you have a delta, which is just the binding energy of the molecule, that one.
So the delta actually on the BEC side is not the binding energy of the molecule. It's actually a weird thing. The only thing that makes sense on the BEC side is delta squared over E Fermi, which turns out is the mean field of an impurity sitting inside the Bose condensate. Delta itself is some square root of E Fermi times the binding energy of molecules. Doesn't have a real meaning. So
nonetheless, do you have a simple model even on the BEC side?
Yes, so here's the story on the BEC side. On the BEC side, this delta is no longer the interesting energy scale, because as you point out, there's now fermion pairing. So never mind my E Fermi over delta, that really comes from BCS. On the BEC side, it turns out the m star minus m here, which is the difference between the effective mass and the bare mass, is still going to be given by all the stuff that can sit inside the soliton. But now the bare mass is also on the same order, right, with the same sign. So that means m star and m will be on the same order. In fact, they will be equal within a factor of 2. That gives you the square root of 2 for the period. So let me say it again. The backflow always gives you a difference between the effective mass and the bare mass, which is given by the full number of atoms that can occupy the region of the soliton. Whereas the bare mass is only the number of missing atoms, which is huge in the BEC regime, on the same order of m star, but tiny in the BCS regime. That's how it goes.
In the case of non-zero temperature, you mentioned that you saw anti-damping, but it went by too quickly for me. Could you say a little bit more about how anti-damping arises in the presence of non-zero temperature?
Yes. Thanks for the question. So,
almost like a setup, right?
It's beautiful. Yeah, thanks, really. So, here we have the anti-damping. We know that the soliton is an excited state of the condensate, because it's not the ground state. The condensate wants to have uniform phase, the soliton has non-uniform phase, so clearly it's an excited state. Now, but how can it find the ground state? Well, it can find the ground state by speeding up. That makes it actually become shallower and broader, and at some point it'll just become a phonon and be gone, right? That's how the soliton can die and the BEC can find its ground state. How does this happen, though? Well, there must be an interaction between phonons that are thermally excited and the soliton. The phonons, they can kick the soliton as they interact with it. And so it's these longitudinal photons that propagate along this long direction of our cloud that will give it a kick and speed it up, and that's what causes then the anti-damping.
Well, Martin, my bias has always been to think of solitons as being almost exactly the same as vortices. You have a phase discontinuity of pi as you go across. In one case, it's a point-like thing. In the other case, it's a line. If you take a vortex and you put it into, say, a spherical or circular geometry condensate, it also oscillates. It oscillates in a circle. And it also has a negative frequency in the sense that in the presence of damping, the circle gets bigger and bigger until it integrates. And in this particular case of the vortex in a harmonically confined condensate, the frequency is actually related to the size of the condensate. It knows something about the size of the condensate. It's almost as if it's being driven by boundary conditions. Is this possible source of discrepancies? I'm just wondering if something like that could be going on in your case.
So here you have me on the spot. I don't know the story that the boundary conditions seem to determine the frequency of the vortex. Here, well, we did check for a few aspect ratios, trying to see whether there's an effect on the trap geometry, at least in the limit of rather longish clouds from 6 to 15, whatever we had a 15% change in the period, we didn't see a huge effect, even though we increased the aspect ratio by a factor of 2. So we think we are in a regime of a very, very long a trap where you can hopefully do some quasi-1D modeling of the velocity field, which doesn't have any radial gradients. So my gut feeling is it doesn't depend on the boundary conditions, but actually it would be fantastic to make a vortex and see how that goes. So.
Maybe this is related to what Eric was asking. At the very beginning, you talked about effective masses and you listed vortices. And as far as I know, all the experiments on vortices in dilute Bose gases, the dynamics, and there are only a few, always obey the equations of motion that are first order in time, so they look as if they have zero mass. And there's been huge controversies over whether there is some effective mass from renormalized phonons or all sorts of stuff, but I don't know of any experimental evidence. And I mean, if you have a simple pancake-shaped disk of radius r, the precession frequency is proportional to 1 over r squared log r. And that's something you can calculate. So maybe that's what Eric has in mind by saying it depends on the boundary conditions. It depends on the size. The experiments agree very well within 5 or 10% of the predictions. And I mean,
I think you just gave the explanation. The log, I think, comes from being 2D, right?
Yeah.
The vortex is swimming in a 2D world where you always have these logs that feel the boundary conditions, whereas in 1D or 3D, you might not. Oh, sorry, r being the size of the...
It's 1 over r squared, basically.
Yeah,
that's bad, okay.
It's 1 over r squared log r, so even if you forget about the log r, it knows about the boundaries.
Sorry.
Well,
Okay.
but you can understand that. I mean, if it was a classical vortex, it moves under its image charge. And when you work out the distance to the image, it always gives you a 1 over r. 1 over r squared.
The image sits outside,
Yeah.
and that's defined by r. Okay, yeah. Seems to be different here.
So I have a comment on this business about boundary conditions and solitons. So one of the ways of thinking about how a soliton oscillates is that you have a soliton. Of course, it's never a black soliton. It's always a gray soliton. Otherwise, it won't move. So it moves, and it moves until the density, the local density, the place where the soliton is, and Eric seems to be agreeing with me, is such that it drops to the point that the soliton becomes black at that point, and then it turns around and goes back. And so it seems like it must know about what maybe not what the borders are, but at least it must know about the way in which the density of the gas is changing, and that, of course, is related to the size of the cloud.
So thanks for that hint. Well, as a function of velocity, it'll be able to climb up this effective hill given by the trapping potential in the superfluid, by different amounts, right? It will at some point come to rest and be dark, which means for us that the gap at that point goes to zero. Indeed, it becomes a black soliton and then turns around. But how far that is of course dependent on the initial velocity. So it's the beautiful property of being in a harmonic trap that this has nothing to do with the size of the cloud.
No, I don't agree. Because what it has to, I mean, the other way of thinking about it is that it just moves until the depth of the original depth of the soliton is equal to whatever what the density is at the place where it turns around. So it does depend on the size of the cloud. And of course, the size of the cloud depends upon the harmonic strength, but it also depends on how many atoms there are and what the interactions are.
Well, that's the beauty of the harmonic potential, right? That you climb up different amounts depending on how much kinetic energy you have, and the size of the cloud drops out. In fact, if it didn't drop out, we wouldn't see sinusoidal motion. We would see some funny, nonlinear, weird stuff. If you give it a big kick, it wouldn't look sinusoidal anymore. If you give it a small kick, it would look sinusoidal. But it always looks very beautifully sinusoidal.
Well, what I'm claiming is that in the same harmonic trap, I can change either the number of atoms or the interaction strength, and this will change the size of the Thomas Fermi radius of the cloud, and therefore change how far the same soliton, the same depth of soliton goes.
We are at unitarity, where the interaction strength is always as large as it can be.
Well, okay, so I wasn't thinking in those terms. So maybe that's the thing that changes things if it's at unitarity. Okay.
I think we better thank Martin, because this is such a beautiful result. Thanks a lot.